Alright, so in this video, we're going to be going over one-sided derivatives. So one-sided derivatives, we'll see, are very similar to one-sided limits, and a lot of the concepts from that section sort of like go over into this concept as well. So let's get into it. So, there's two ways and two main uses for one-sided derivatives. So let's say we want to talk about a function. Let's say we want to talk about a function f on the interval a comma b, and we say inclusive, that's why it's like a bracket, so ab inclusive. So a function f on the interval ab is differentiable on the entire interval if there exists a derivative at every point on the interval not including AB, and the right hand limit at A exists, and the left hand limit at B exists. Alright, so what are these right and left hand limits? Or the right and left hand derivatives, derivative. I got ahead of myself. So what are right and left hand derivatives? So let me just draw the said function. So let's say we have this function, right? And this is point A, and this is point B. So we're saying that a derivative exists on this entire interval if a function is differentiable on every single point from A to B on that interval A to B, not including A and B, because you can't, recall the definition of derivative. If we try to use that on B, right, we have to do like B plus some H, but we don't have that, right? And then similarly, we don't have anything before A to sort of get the derivative too. That's why at endpoints we use one-sided derivatives. So again, if a function is differentiable on the entire interval A and B, if a derivative exists on the interval A, B, where A and B are not included, and we have the one-sided limits on A and B. So what is the right-hand derivative at A? So that's defined as limit as h tends to 0 from the positive end of f of A plus h minus f of A over h. So this is right hand derivative, and then the left hand derivative is limit as h tends to 0 from the negative end of f of b plus h minus f of b over h, and this is the left hand derivative. So how do you make sense of this notation? So notice that if we have a function, right, at point A, if we want to find the derivative, what we need is we need to anchor the point at point A, and then we have to keep checking, we have to keep going from various points of the function, like at A plus some delta, and we have to decrease that delta to A, right? And in the process of doing that, our h, which is our delta, is basically going to get smaller and smaller. It's going to get towards 0. And since we're starting from an n that's greater than a, our delta is going to head to 0 from the positive end, because it's going to be some positive delta, and it's going to become smaller and smaller. So we're going to head to 0 from the positive end. On the flip side, right, if we anchor a point at b, and we have some b, our delta is negative, right? Notice how it's a minus delta. And so the delta keeps increasing because we're going from like a negative number to 0. So like, the smaller the magnitude of the negative number, it's greater in size, right? Because -2 is less than -1. So yeah, our delta is increasing, and because the negative value gets less and less negative, we're going towards 0 from the negative end, right? So hopefully that makes sense. And I know a lot of people get confused between the right-hand derivative and the left, because here this is a left-hand point, but we need the right-hand derivative. An easy way to remember it is just like, just remember that we do the right-hand derivative when we're just going from like our right side towards the left, and then we need the left-hand derivative when we're going from the left towards our right endpoint. And hopefully my explanation of why this is positive here and this is negative here should be pretty clear and should help understand if there's any confusions. And so recall that when we're defining limits, we said the limit of a function at an arbitrary point. So let me actually just switch the page. So recall that we said from limits, right? If the right hand and left hand limits are equal, then the limit at point x exists, right? And so this goes, this sort of alludes to our second use of our one-sided derivatives, right? Because you know how part of our sort of definition for a derivative existing on the interval AB is if on this interval, this entire interval, we had a derivative existing, and we had the one-sided derivative existing on A and B, right? And how do we know that our derivatives sort of exist on this exclusive interval? And that basically goes, that we know by translating an analogous definition. So our analogous definition is if the right and left hand derivative at point x are equal, then the derivative exists at point x. All right. So that sort of tells us a way to see how a derivative, whether a derivative exists or not. And let's just put this through the test with an example. Let's say we're given a function, right? That looks like this. We have a linear line, and then we have a curve. Oh my god, okay. We have a curve, right? And so this is a piecewise function, and it's defined as y is equal to x squared if x is less than or equal to 0, and y is equal to 2x if x is greater than 0. So we have to verify that no derivative exists at 0. So verify that the derivative of y at x is equal to 0 is undefined. And so for this, we use the concepts for one-sided limits. So let's find the left-hand derivative at point equals 0. So limit as h tends to 0 from the negative end, because left hand means we're going from the left to the right. 0 plus h, again I'm plugging in 0 for x, minus 0 squared, we can square this all over h is equal to just h, which is 0, and then from the negative side, and then limit as h tends to 0 from the positive side, and this is our right-hand derivative, and we're going basically from the right to the left, and so it's this function, right? Previously it was this function as we're going from the left to right, but from right to left it's a different function that describes a different piece that describes the whole function. So then for that we do 2 times 0 plus h minus 2 times 0 divided by h, and that is equal to 2h over h, and then that cancels, so we get 2. And we clearly see that 2 is not equal to 0, and because our one-sided limits differ, we can verify that the derivative of y at point x equals 0 is not defined. And yeah, so hopefully you guys understood what one-sided limits are, and how they're pretty analogous to one-sided limits. So hopefully the one-sided derivatives and one-sided limits, because they're analogous, it shouldn't be too hard to transfer the concepts over.